Hello. Today I know that we are going to have a discussion on the master theorem. The master theorem is a mathematical tool used in the analysis of algorithms, particularly for analyzing the time complexity of divide and conquer algorithm. The master theorem is usually expressed in the following formula: Tn, Lt, and divided by plus Fin. In this formula, Tn represents the time complexity of the algorithm. A denotes the number of the subproblems. B indicates the ratio, representing the ratio of the input in each subproblem. Fn represents the additional operation count performed by the divide and conquer algorithm. Using this formula, we can analyze the time complexity and algorithm. However, it does not cover all cases and is applicable to specific scenarios. Today, we will start by applying this theorem with a simple example. First, we will encounter a master theorem question, and you will take a step to solve it. If you find it challenging, you can share your partial solution and request the quiddance instead of a complete solution. Next, we will move on to recurrent relation question, providing insights into how algorithm works sequentially. If you can handle this basic level question, we will progress the more complex medium level question. Then we will challenge you with the most difficult ones. At the end of the day, we will turn this discussion and problem-solving process into a YouTube video. We can share this video to help others learn about these topics. Let's get started and have a fun learning day. Before we begin, do you have any questions about what the master theorem is and how we can solve a basic example? Let's. This is my homework and because I try it. I write, can you give me basic practice question on the master theorem? Yes. Thank you, ChatGPT. Yes, ChatGPT said, consider a recursive algorithm with the following recurrent relation. We are dividing into the master theorem, a powerful tool for analyzing the time complexity of recursive algorithms. Let's work through a basic practice question to get a hands-on understanding. The master theorem is often expressed as Tn equal AT and divided B plus Fn. In our case, A equal to, because we have two recursive calls, B equal to 2, since the input size is halved in each recursive call. Fn equal N represents the non-recursive work done per level. Now, the master theorem has three cases. If Fn is O and C, where C or two cases in however, let's apply this recursion relation. Tn equal to Tn divided 2 plus m. We calculate log 2 equal 1. Size Fn equal m is O and C where C equal 1. We fall into the first case. Solution. This question solution. According to master theorem, case 1, the solution Tn equal On log 2 equal On. Thus, the algorithm's asymptotic time complexity is On. And there you have it. The master theorem helps us to understand the efficiency of recursive algorithms by providing a framework for analyzing their time complexity. Yes. And I solved the problem. Yes. We have a Python script that walks us through the solution of the recurrence relation using the master theorem. Let's break down the key components of this script. We have function cal master theorem example. Yes, see it. That takes 4 parameters t. Yes. T, the recursion relation, and A, B, and F representing the coefficients and function in the master theorem formula. Yes, I write it. And the first step to calculate the logarithm ratio, log B, which is the exponent in the regression relation. This is done using the MATLAB function in Python. Yes, and this is, you see it. And next, the script checks which case of the master theorem applies based on the provided function fn. And finally, this is your scene print. Finally, the script prints out the given recursion relation, the master theorem formula, the calculation of the logarithm ratio, and resulting solution. And the script concludes by testing function, the sample regression relation. Yes, apply it. Okay. Yes. Given the recursion relation, Tn equal 2 multiple Tn divided 2 plus n, master theorem Tn 2 Tn divided 2 plus n. Applying the master theorem, log 2 equal 1.0, solution Tn equal On. I'm sorry. Yes. And this is it. The script is handy tool for applying master theorem, the theorem to analyze the time complexity of recursive algorithm. If you have any question or if there is anything specific you would like to explore the future, feel free to let me know. Yes, as I said, do not hesitate to ask me, my dear YouTube followers. Now we move on to our mid-level question and ask, but I ask it. Yes, I ask, is this answer? Let's see. Okay. However, it seems too small. Yes. Small mistake in your recursion relation application master theorem. Let's correct it. Yes, this is the correct one. tmb, the function, to write it, and log b to, okay. Thank you. This solution. Okay. Last middle one, basic practice question. Middle practice question, master theorem. Thank you, ChatGPT. Yes, imagine you're dealing with a problem that breaks down into smaller pieces. Each time you split the problem, I end up with 4 sub-problems, and there is a bit extra works added at each level. Now, think of the first problem is growth. If you double the size of the problem, does the total work more than double? In the case, yes, because there is an extra amount of work and square at each step. So, the more you increase the size of the problem, the more the total work shuts up. It's not just doubling. It's more than that because of that extra work factor. The master theorem is like a quiz that helps us practice how fast the total work grows. In our case, it tells us that the total work will grow as n square. If the original problem takes a certain amount of the time to solve, when you make the problem twice as big, it will take more than 4 times in the initial time because of that extra work. It is a bit like saying, as the problem gets bigger, the time it takes grows really quickly. So, without getting into the nitty-gritty of the formula, we can say the solution something like, the time it takes is proportional n squared. Yes, I solved the collaborative and the master theorem example. In this Python code, we are implementing a recursive algorithm based on specific recurrence relation. The relation is defined as Tn equal 4Tn divided plus n squared. This means that total work for a problem of size n is determined by 4 recursive calls, each working on problem of size n divided 2 plus an additional n squared work at each level. We have created a function called master theorem example to model this recursive behavior. It takes a parameter and representing the size of the problem. Yes, you see it, def master theorem example if n and if the problem size n is 1 or less, we assume the work is constant and return 1. For larger problem sizes, we perform 4 recursive calls and subproblems of size n divided 2 and add the extra n squared work. We then test this function with a specific input n equal 8 to see how much total work is recurred for a problem of that size. Yes, the result will give us an idea of the total work we needed to solve a problem of size 8 using this recursive algorithm. Yes. Play it. The total work for a problem is approximately 200. Sorry. I think the total work for the problem approximately 7. Anyway, the result is the total work for the problem is approximately 256.0 yes copies. Is it true? Size for yes, the correct value is I don't know. I don't know. Solution, please. Solution, please. Yes, given T1 approximately. To indicate the mistakes in calculation, interpretation, steps calculation, and specification. Thank you. ChatGPT. I'm understanding. And the hardest one. Thank you. Yes. Imagine you have a problem and you are solving it using recursive algorithm. The algorithm follows a pattern defined by recurrence relation. Tn 16 plus Tn divided 4 plus n squared log 3n. You are dividing, I am dividing the problem into 16 smaller subproblems, each dealing with a quarter of the original size. At each step, there is some extra work involved, and this extra work is proportional to n squared log 3n. The key question is how does the total work grow the problem size increases? It turns out that the growth is dominated by the term n squared log 3n. Now, compare this growth pattern to Knopf patterns. The growth is similar to n squared log n, and this is the dominating factor. In simpler terms, as the problem size increases, the time it takes grows in a way that's like proportional to n squared log n. So, without dividing into the mathematical details, we can say the solution's time complexity is rarely n squared multiple log n. Yes, I solve with the collaborative, and I explain this formula. Yes. Here we are building a Python function as a solved problem based on a given recurrent relation. The relation is defined as Tn blah blah. We have defined a functional named master theorem example that models this recursive behavior. It takes a parameter and representing the size of the problem. If the problem size n is 1 or less, we assume the work constant and return 1. For larger problem size, we perform 16 recursive calls on subproblem of size and divide it for and add an extra n squared log 3n work. We then test this function with a specific input n equals 16 to see how much total work is required for a problem of that size. These results we give as an idea the total work needed to solve a problem of size 16 using the recursive algorithm. As I played. Yes, thank you. And copy it. Let's define with the identity solution. Okay. And approximately 3. Please double check calculation. Are you complex algorithm goes. Yes, and this is it. Okay. Yes. Because let's see it. This is my homework video, and thank you, ChatGPT. ChatGPT. Let's look at my my YouTuber. Thank you. You see it and listening. And Bye-bye.